This lecture is about embedded system design for automotive application, which will be mainly comes under electronics applications of FPGA. Nowadays, if you see the recent cars, it has completely embedded software, mechatronic system, wire harnesses, PCBs, which includes all the integrated system designs, then FPGAs and signal processing, and integrated circuits, which will need design verification and manufacturing of everything. Actually, a modern vehicle contains more than a dozen and nearly 100 electronic control units. So the current electronic systems are partitioned into domains such as real-time hard control of mechanical parts and the information entertainment. So the first category is controlling of electronics and mechanical parts, which will be having chassis control, then automotive body, which includes interior air conditioning, dashboard, power windows and control subsystems, and then the power drain, which includes the engine, transmission, then emission of smokes and further control, brake control and all other controls, and importantly active safety control. So you might have seen when the door is opened, the car will not be able to start, and you will get the alarm indication saying that the door is open. So this is and all to ensure the active safety control. The second category is mainly for the entertainment or information management, which includes the navigation, then computing, then external communication, entertainment. So we'll be seeing one by one. So each domain has its own computation speed, time and reliability and extensibility. So today powertrain applications most demanding challenge in terms of real-time constraints and the computational power, which we need to engine speed, we need to take care of the engine speed and the power aspect, everything. So first we'll see automotive embedded computing system. What is embedded computing system? A small computer system itself embedded in a piece of equipment or in a machine to control it. That is embedded. So embedded systems are mostly applied to electric or electronic equipment. So if it is an automotive embedded computing system, a computer system that is embedded into the car to control it. So the embedded computer unit is called an ECU, electronic control unit. So if you take an example, Lexus LS460, which is released in September 2006, it has more than 100 ECUs, electronics control units, which is embedded inside when all optional equipments are installed. So about 70 lakhs lines of software coding is been embedded, which is from different. So if you see the electronic control unit, which is being fitted in the car fully, you can able to see it on the doors, on the window and on the tire systems and on the engine systems and on the chassis, everywhere. So general features of automotive embedded systems. As many as I told, 100 ECUs are used for the following purpose. What are the purpose? Energy saving, first of all, energy saving, and then low emission, then safety, either active safety or passive safety, then comfortableness, convenience, entertainment, and mainly for cost and weight reduction. ECUs are connected with the several in-vehicle networks, so it should ensure high reliability and safety requirements, and strict real-time property is required. So severe environmental condition like temperature, EMC, all things should be taken. Severe production cost. ECUs for different system services have different requirements, different technologies. So classification of what are the automotive embedded systems? We have powertrain and chassis control, which is included with the engine, automotive transmission, hybrid control, steering, brake, suspension and all. Then body electronics will include the panel, key, door, window, lighting, then airbag, seat belt and all those things. Then when comes to the multimedia, which will be the information and entertainment, which together called infotainment application, we have car radio, car navigation, then information about the traffic, then toll collection, electronic toll collection, back guide monitor. When you are taking the reverse, it indicates the back, so it will act as a back guide monitor. Integrated systems and services, which includes electronic stability control, the car stability, then pre-crash safety, vibration and all the pre-crash safety, then parking assistance, lane keeping assistance, all the things which are the integrated system services. Engine management system. What are the engine management system units or system components? It has a control computer, which is electronic control unit. Then it has many sensors, which get activated based on the functionality or based on the place where it has been mentioned, where it has been implanted, and give the information to the monitoring unit, and the monitoring unit will give the information to the control unit, so that it has been controlled. So many sensors will be incorporated in crank position sensor, airflow meter, temperature sensor, throttle sensor, some other actuators. Basic function of the control system, it is what are the main things? It will calculate what is the fuel injection volume, what is the ignition time, what is the control, what is the RPM, what is the rotation cycle, includes all the things. The second one is mainly anti-lock braking system, we shortly called as ABS, anti-lock braking system. So the speed of the car and the rotational speed of the wheel are monitored. So whenever there is a possibility of skid, or whenever the skid is detected, okay, the brake is been applied, so it avoid the collision. So when a skid is detected, hydraulic pressure to the brake is reduced to stop the skid. So the system is relatively simple, but is becoming more complex and recent. So it ensures the safety requirements, and continuous reduction of hydraulic pressure causes the non-braking actually. So if some fault is detected, ABS stops functioning, then the brake works through the skid can be avoided. Then comes the airbag control. The function of the airbag control is whenever the car gets collided, okay, so to save the person an airbag gets open so that he saves from collide with the window shield. So airbag control system monitors various sensors including the accelerometer and detects a collision. So if a collision is detected, the ignition of the gas generator propellant triggered immediately to inflate the bag. So it must be triggered within 10 to 20 milliseconds after the collision. If it is more than that, then no use. So within 10 to 20 milliseconds, the collision bag, the airbag get inflated, and it will save the people here to safeguard from the collision. Fail safe cannot be applied. Integrated system, as I mentioned, what are the integrated systems in vehicle dynamic integrated system? It will have a control brake, steering and engine for avoid slip and spin. So it will control and monitor the steer angle sensor is there, brake pedal stroke sensor, brake pressure sensor, then ECB wheel speed sensor, wheel aligning, yaw rate and acceleration sensor to maintain the wheel balance, then electric power steering actuator, then torque sensor for maintain the speed. So all those things are integrated system services which is included in all the places mentioned here in the diagram. Then comes the pre-crash safety system when an obstacle is detected in front. So with the stereo camera, there is a camera here. So with the stereo camera and the millimeter wave radar arrangement, okay, the system retracts the seat belt, it warns the driver and applies the brake. So it's a very good mechanism to save the crashing. So when an obstacle is detected with the stereo camera and millimeter wave radar, the system retracts the seat belts, warns the driver and applies the brake. Driver's condition example face direction is monitored. So here is the stereo camera and driver monitoring camera, collision determination electronic control unit, then pre-crash brake. So this brake is been applied automatically. So suspension control, steering control, near infrared projector, millimeter wave radar which projected from the car towards the obstacle. So from that analysis the pre-crash system will work to avoid the collision. What are the current problems of automotive embedded system? It has a complicated system design which increase the development cost and time, and high reliability and safety is an important issue. Large scale and complicated software, highly complicated software, and how to reuse the software, and too large number of ECUs which will increase the cost, and insufficient space in the car for the ECUs, then complicated network architecture which will increase the complexity. Platform based development, conventional component based development, each ECU component is developed usually independently. So each electronic control unit is developed independently, later on it is being assembled. An automotive component supplier develops both the hardware and the software for that particular ECU. So the car system is designed by integrating all the ECUs developed by different suppliers. So the platform based development should be developed at first. So it should be a hardware platform plus software platform plus networking of all these things. So the software platform will include the OS plus middleware. So the application software should be developed on the platform. So AUTOSAR, which is Automotive Open System Architecture. So it is a global partnership of car makers, car component, electronics, semiconductor and software industries, founded in 2003. It defines a methodology that supports the different function driven development process. It standardizes the software used in the car ECUs. So the partners will be BMW, Porsche, Continental, Daimler, Ford, GM, Toyota, Volkswagen, etc. So the resultant current status as a recent version consists of about 100 specification and 80 related documents. Then the activity was started in 2010. Next activity is started in 2010. What are future trends of automotive embedded system? Advancement in the integrated system services. So in future there may be a communication with one car with the another car on the road, so that they can maintain the distance between them and all other communication using various information. So this is where people work on IoT, Internet of Things. So using various information like surrounding the situation and map information for controlling a car, then emergence of true by wire systems, then changes in the architecture means EC integration, okay, or reduction, then platform based development, then separation into two types of ECUs, then changes in software development like model based design, component based software design, then virtual platform for software development. So this figure outlines the additional intricacies in the automotive design chain. the systems are so complex that there are two kinds of subsystems: the actual OEM, that is original equipment manufacturer, that produce a car, that will be the first one, and then the tier 1 suppliers, which is from the semiconductor industries. They will have the licensed IP system on chip subsystems, and then they integrate them into the subsystem board level, including in all the electronic control unit. So original equipment manufacturer will make the vehicle as such, so it's a vehicle. Then what happened, the OEM tier 1 people will create small subsystems for the car, and then tier 1 people also create ECU, electronic control unit, then mechanical control unit, so they all will be fitted into the car. So this is a original equipment manufacturer, and these are the additional suppliers. So in present day car system, they play a equal role. The vehicle manufacturer is the FPGA based or the embedded processor application people play a equal role with the car manufacturer. So it includes software scope, it includes application layer, middleware, and services, and ECU abstraction, then mechanical control unit abstraction. So all the things been included in that. There are other consumer applications where mainly embedded electronics is being used: printers, audio systems, karaoke microphones, scanners, scanner, printer, all integrated one. Then obviously the car and missiles, Astro H missile, then Xerox music, and soldering machine, and all other equipments, which also include embedded applications. You see an article which explains about the forging ahead into the consumer applications. So the FPGA is actually tremendously used for various applications, which will be useful for making the prototyping tool, and number of embedded processors are now enabling the new technologies. So it is mainly used in the military, aerospace market, and other FPGA vendors are like capitalizing the most with the FPGA company. And most of the electronic consumer segment become now standby mode. They run a device lower power than the CPU or a GPU, and the consumer devices are mainly using the FPGA includes the cost cutting. So consumer application hold promise for FPGA. The smartphone market promise fairly for FPGA applications. Same as tablet opportunities, FPGAs for iPad, Apple, Samsung Galaxy, all the people the potential area where low power FPGA could help Samsung distance its Galaxy from the iPad. So an FPGA also need a rich ecosystem of partners, and the main evolving FPGA vendors in the market: 34% debuggers, 31% compilers, then 29 editors, then software system modeling tools, in-circuit emulators, dynamic software testing tools, then security management tools, virtual platforms, model-based software testing tools, static analysis tools, and building the tools and simulators. So this is a potential tool ecosystem for FPGA development in the upcoming market. So both the mobile industries and Lattice recent partners with the Texas Instruments, Qualcomm, and mobile industry, they are the potential marketing persons for the FPGA. So having a robust ecosystem, the real differentiators are hardware, which is increasingly becoming a commodity, and software, which determines the time to market. So great example is Xilinx. As a large vendor, Xilinx we can choose from a board ecosystem, and so the figure which I shown is highlighting the kinds of tools that developers are using for their consumer project. Consumer electronics mainly drives the FPGA growth. So in 2020, the FPGA market will reach 9,882.5 million by 2020. So the key growth driver over the next years is mainly the consumer electronics, which includes the smartphone. The report also says FPGA market analysis by application of automotive. That's what we have seen: automotive, consumer electronics, data processing, industrial, military and aerospace, telecom application, and the segment forecast to 2020. Also finds a growing electronic content in automobiles, along with further adoption of electric vehicles themselves, and hybrid electric vehicle will contribute to growth over the forecast period from 14 to 20. So the consumer electronics accounted for more than 12% of the market in 2013 and will be expected to grow faster than the global average. So the telecom is expected to remain the largest and the fastest growth application for the consumer electronics. One of the biggest factors spurring FPGA demand across application is this miniaturization. According to the few of those growth opportunity application includes wireless networks, medical imaging, and particularly medical imaging poses a growth opportunity because of the FPGA offering a high degree of flexibility and reprogrammable. That's more important, reprogrammable and reusable. So as viable FPGA substrates may hamper growth over the next 6 years according to the report analysis. Xilinx and Ultra continue to retain the leadership in the FPGA market. One case in point is Ultra FPGAs with embedded CPU architecture for storage in the cloud and high performance computing. The company's new storage reference design is 10 SoCs, said to be double the life of NAND flash and can increase the number of program erasable cycles. So reuse factor is more now. So if you see the targeting growing automotive electronic market, new family of automotive grade SoC FPGAs and smart fusion devices, everything has been achieved because of this. The automotive market for semiconductor is 31.4 billion in 2015 from 29.4 billion from 2014. So such a huge increase in the automotive market industry, an increase of almost 7%. This is one example of FPGA based design and performance analysis of wireless sensor network. So it is having a transceiver, which is transmit receiver, and a microprocessor external memory, which is being powered by this power source. Then analog to digital converter, sensor 1 and up to n sensors. This is the sensor node architecture. Then the representation of emulated design different functions from the n number of sensors, function 1, function 2, function n. So they are all been multiplexed, and the display is given the LED, then the sound segment. So the design flow is design entry, then system modeling, simulation and verification, and if it is the simulation and validation is okay, then proceed for the technology mapping, then hardware implementation. If not, then go again for the design entry satisfaction. So it has been implemented with the FPGA Spartan 3 development board. So the same thing, transmitter node block diagram is being implemented. The sensor and ADG sensor will give the analog signal, which will be converted to digital by this. Then it is given to the FPGA board. So inside the FPGA board, the logic block, the clocking, and the transmitter all will be written as a program using the Verilog. So the RF module is external one. Then we have in the receiver node RF module, then the complete FPGA board, which includes the logic block and the clocks and receiver, and the data will be received.